Oh.
Those pictures from what Saturday a month ago.
Right. Right now. Loading. You ready for this? Yeah, I don't know any of this. Yo, I just need a B.
You shit.
I can't just try to pass. I have to get a B. I don't care if I get a C. I don't care if I get a D. As long as I pass.
It's not
passes.
possible.
Huh? It's not. It's not for me. Yo, Pranava.
Okay. Hi.
Let's say we get a D in this class, right?
Okay.
Like, is that considered passing?
Not for financial aid.
I am not sure actually. I can check, but I'm not sure. I think so, but I'm not sure.
If you've got federal financial aid, they don't consider it a completion, and you end up on probation.
Okay.
Yeah, anything below it too.
See you guys in probation, guys.
Okay, I think we're ready. There is one student online, two students online. It's not bad.
Get on. I got you.
So if you're going to talk something, it's going to be recorded.
Listen.
Yay, we're being recorded.
Wait, so if I like get on there and I ask you a question, it's recorded?
No, I'm saying if you
Here?
talk right now,
It's recorded.
yeah, it's being recorded right now. So.
Yeah, there are microphones. We're being broadcast. Hello.
Oh, it's being shared. Oh, that's what. Okay. Good. Okay. Let's see. So I'm going to talk about the questions that you are given as practice in Blackboard. So, do you guys have the questions?
Yep.
All of you right now?
Well, just saying.
Well, I'll read it out anyway. Let's see. So the first question is, in a spacecraft of mass 3050 kilograms, Buzz Lightyear orbits a planet of mass. Let me write down the name. This is.
I think you have to select the color.
You need a padding for the top right.
It's going to be really embarrassing for you, Pranava.
Yeah, I know, right? I look so stupid. Oh, hey.
You're going to lose viewers.
I'm so worried about the.
Because you still have the pen in your hand.
Yeah.
You can't have both.
I.
And you still
I have to
clicked on
pick
it.
the
You
eraser.
have to click on the eraser. There you go.
Okay. Now that we have solved that issue, let's solve problems. So the mass.
Smart board. I was supposed to do physics.
Oh. Okay, good enough. As long as it's understandable. So the mass of shuttle is 3050 kilograms. The mass of the planet is given as 7.05 times 10 to the 25 kilograms. And the orbit that Buzz Lightyear is moving around has a radius of 4.25 times 10 to the 7. So the first question is find the period of the orbit. There is a formula directly, but let me derive how we get the formula. So I'll walk you through the steps. You'll also get to know some other things while I'm doing it.
Are we gonna have to derive it on test?
No, you don't have to. I'm
Okay.
just saying.
Alright.
It's not long. So that's not an orbit, but I couldn't do better than that. So that's the orbit. So the force on Buzz Lightyear, the shuttlecraft, is there are two forces. One is not two forces, one force, which is centripetal force, which acts. Okay, you have gravitational pull, which acts as centripetal force, keeping him in the orbit. So I can write the force due to gravity, which is given by G m over r square, where G is gravitational constant, capital M is the mass of the planet that the craft is moving in around. Small m is the mass of craft itself. R is the radius of orbit. That will be acts like the centripetal force. So m r omega square. Where m is again the mass of the spacecraft. So I can get rid of this, and omega is equal to G capital M over R cube whole square root. That's the angular velocity of the angular frequency of the rotation of spacecraft around the orbit. We were asked for time period. Let me just derive something else here. That means implies omega is V over R. We know that omega is V over R. So let me just derive the value of V. So V from this formula is over. So V is this multiplied by R, but when I take R into the square root, I'll get an R square inside the numerator. So that's basically what V is. This is a sine. Oh, I see. Okay. So yeah, we derived that omega is equal to square root Gm over R cube. But omega is equal to 2 pi over time period. Or you could also, there is also another formula which might be helpful, is 2 pi times the frequency. So using this equation and this equation, you can derive time period is equal to, when I equate this to this, I can write time period is equal to 2 pi square root of R cube over G M. Yeah, that's the time period. Actually, I need help from someone of you. I need one of you to calculate the values, so that I don't have a calculator. I can tell you the answers. This one?
No, above it.
Oh, square root of gm over r square.
And then right below it, right here, it's like B. What does that say?
Oh, but. Okay. That doesn't, that makes it worse.
Like, are you talking about Buzz Lightyear?
Okay.
Buzz-
Yes, Buzz Lightyear is the first one.
Oh, okay. So it's minus.
Mhm. This one.
Okay.
I'm just, this is stepwise.
Okay.
Omega is something that I've derived, and now, since we know that omega is 2 pi over time, I'm equating this omega to that omega,
Okay.
and I'm deriving the value of time period.
Wait, didn't you say that there's an equation for the time period?
Yes.
directly?
This is the equation. I just derived.
Okay, because that one's not on the equation sheet. The only one that's on there is it's a squared equals 4 pi squared over gn times a cubed.
Yeah. Because it's wrong. It's not A, it's R cubed.
Oh,
R is the radius. The A is
And it's semi-major axis, yeah.
semi-major axis.
But
Since we are
calculated
considering the circular orbit,
Alright.
it's the same. Yeah, so that's the time period. And do you have an answer? Wait, actually, I think I yeah, so it's 12.
24,386.
Seconds, that's in seconds. And when we do it in hours if we want, okay, 7.0 hours. So remember how we did everybody copy write it down? So remember how we derived the velocity? So that's for the second question. You're asked for the speed of shuttlecraft, and that's the formula we use for speed of shuttlecraft. I just oh, oh, I see.
What is the value of that?
Sorry?
Did we calculate that?
Yes. No, I mean we did not calculate it. I just derived it and then. I'm going to calculate.
What was the answer again? Oh,
Oh, yeah.
25.
Is it
You don't really need the answer.
Is it 705 hours?
No, 7.05 hours. 7 hours.
You said we don't need answers?
Well, it's because
You don't, you need the solution.
Yeah.
Well, the answers, unless the same thing happens like last time.
Let's hope.
In which case, people who are missing are in a lot of trouble.
Is he going to be putting these solutions online before?
Did you see what he said? He is like, it's gonna be posted like in May or something.
Oh yeah, that's right. I did see that. I saw
May?
that. Yep. It says online it's posted in May of
Oh, this one?
2014. So I mean, it should have already.
Was that an email?
No, I just saw it on Blackboard.
Wait, what?
I think he's just probably posted it
Yeah.
another year and then just
Yeah.
like.
And the fact that he's redoing that gives me hope we'll have the same chance.
Okay, anyway, so let me just tell you what the answer is. You all can, I have confidence you can do that part.
So you're doing B now?
Sorry?
That
The velocity, yes, B. So that's the answer. Okay. Part C asks for total mechanical energy in the orbit. So when we speak about mechanical energy, it is sum of kinetic energies and potential energy. So let me call T as the total energy, total mechanical energy. That's K plus U. K is the kinetic energy, U is the potential energy. We know that K is half mv squared plus. Remember that potential energy is Gmm over R, but remember that it's always negative. So you will have again, if you see the equation sheet that I don't have the equation sheet, but sometimes you might have notation a little differently. Make sure that you write them down what they are now, so that you will have.
Why didn't you do the
Oh, yeah, true.
K.
switch?
Let's make it look good.
Why
One
didn't you do the gravitational kinetic energy if you did the gravitational potential? Because it has the equation G m1 m2 over 2r for kinetic.
That's the total energy, mechanical energy. Oh, yeah. Okay. I'll tell you why. When we substitute V from here, we'll get Gm m1 m2 over 2r.
Oh, okay.
Again, remember that this m is the mass of the planet, or was it planet? Yes, planet. And that small m is the mass of the spacecraft.
Okay.
So from here, using these two equations, I substitute V is equal to Gm over R there. I'll have Gm over R is equal to Gm. So that was what you're talking about.
Yeah.
Yep. Let's use that. Which means total energy is sum of kinetic and potential. So we'll have G m over R. Actually, 2R minus G m over R, and that is equal to minus G m over 2R. That's the total mechanical energy. If you have a question of why the energy is negative, it's because it's essentially our reference. We take infinity as 0 for potential energy. That's why any point other than infinity, you have some negative energy, and which is what gives it the negative energy, negative total energy. And it says in the question, actually, assuming standard 0 point for orbital gravitational potential energy, which means infinity is 0. Okay. The fourth question is, if Buzz fires a thruster to increase the velocity of shuttlecraft by 48%, will he be able to travel to infinity and beyond?
Is it 48%?
48.
Percent, though.
Yes.
Good lord.
Let's see. So there is a formula for escape velocity, something called escape velocity, but we can still derive it. It's pretty straightforward. So when you have enough energy, when Buzz Lightyear has enough energy to escape, he'll end up in infinity, which is zero potential energy, and the minimum energy required to go to that point, well, not required, but at infinity, Buzz Lightyear doesn't really need to have any kinetic energy. We need kinetic energy when he's moving and when he's being thrusted, but at infinity, he doesn't need any kinetic energy. So what we use to derive what's the escape velocity is we say we use conservation of energy. So we say the energy when he's going around in the orbit is the same as energy when he's at infinity. So the energy, when I say energy, I mean total energy. I've never seen you guys paying so much attention, not even in the labs. Yeah. So half m. So the only difference now, when you have a thruster fired, there is an increase in velocity, and I put a suffix e to tell that that's the minimum velocity that's needed to go out of the orbit, which is escape velocity. So this is the kinetic energy, and you have a potential energy, which is Gm over r. And like I said, this energy should be equal to the total energy let's say at and for the quirky ones among you and beyond is equal to zero kinetic energy, because we just need him to go to infinity, not more than that, plus zero potential energy, because I said at infinity the potential energy is zero. That's where we put our reference to it. So I equate these two, which gives me 2Gm over R. If you remember, the velocity that he's actually moving in the orbit was, let me put it here as Gm over R. So the additional velocity that is needed is that minus that, right? So this is the velocity needed for him to go out of the orbit. This is the velocity that he already has. So the additional velocity that is needed is not eraser, e minus v, which is square root of 2. Let me just write it down. Write this down. Oh, that's just sad. So we know that square root of 2 is 1.412 with 1.4, and that's 1. 1.4 minus 1 is 0.41, and which means the ratio, the additional energy needed for Buzz Lightyear to go out of the orbit is 41% of what he already has, which means the 48% is more than enough for him to get out of the orbit and beyond. Was the last part clear, or did I just run through it? Okay, let me explain.
So we just find this value and make a percentage of what he already has.
And this comes out to be 0.41, which is a fraction, the 41%.
That's the minimum.
Yeah, this is the minimum amount. The question asks for if it has a 48%, does he go out of the orbit? Yes, he does.
What does V escape calculate to me?
Sorry, what does?
The value?
Yeah.
You don't have to calculate it.
I mean, you can calculate it, but
14,000.
Because it'd be easier to just compare the numbers.
Yeah,
Right?
it's 14,870.
okay.
Okay.
And then he increases to 15,566.
That's not 40%. Increases to or by?
Increases
Two.
to,
You said 15,000?
Yeah.
yeah, increases
15,000.
from 10,000 to 50.
Or 10,000?
Or from 10,518.
I see. Okay. That makes sense. The second question is simple bob pendulum, and the period of oscillation is given, which is, we know that we always write time period as t, 1.5 seconds. You are asked to find out what angular frequency is. So there are two things it's good for you to remember. I don't know if you have them in the equation sheet, but omega is square root of G over L for and just because we are talking about angular frequency, let me just write this down. And G you know is gravitation 9.8. Acceleration due to gravity. L is the length of the pendulum. K is the spring constant. M is the mass. Mass of whatever is attached to the spring. What was the question? Oh, angular frequency. So it is pretty straightforward to calculate this.
So we don't have the length. It's 2
Oh,
pi
that's
over
good.
2 pi over 3 over t, right?
Yes. Yes, we don't have the length. But we know that omega is 2 pi over time period. So we know what time period is, which was 1.5 seconds. So you will have 4.2 radians per second. Okay. So always remember, radians is dimensionless quantity. So essentially the dimensions of that is 1 over second. That tells you how much of an angle it has gone through in 1 second. Really?
That's low.
That's beautiful. Oh no! I don't know how many additional pages are added. That's for the rough work. The second question is length of pendulum. So we know omega is 4.2 radians per second, and we also know that omega is square root of g over L. And assuming that we are on the Earth, assuming g to be 9.81, L is equal to, I can square on both sides, take L to that side, take 4.2 to this side, so it will be g over 4.2 whole square. Uh, 9.
So,
Point 7,
56.
56 centimeters. Now, imagine that you take this pendulum to a different planet. You displace it as before, but now observe the period to be 0.41 seconds. What's the acceleration due to gravity on that planet? So you are given the time period, and you know the length of the pendulum. The pendulum is not changed, so the length remains constant. We can still use the same formula. L remains the same, except G, let me call it G1, the gravitational constant on that planet, the acceleration due to gravity on that planet. So we know what time period is, it's given as 0.41, and we know what length is.
So can you just multiply length times the new period squared?
No, but the angular velocity.
Or
Oh, my
yeah,
bad.
you divide length, right?
Yeah.
Okay, you'll get this 4 pi r square L over G square, sorry, P square. I just thought I was getting good at this. Right. Yes.
I went through the procedure the same as the second one. I'd find the angular velocity,
Mm-hmm.
and then instead of inserting the gravity, I would insert the length and find the gravity from the square root of L over G formula. Is that okay too?
Yeah.
Okay.
Is that 4 pi squared
Wait.
L?
Can you repeat that again?
So I would find the angular velocity first,
Okay.
the new angular velocity, and then I would,
How would you find it out?
because I have time periods, so 2 pi
Okay.
over T.
Okay. Yeah. Then it's.
And then I would use angular velocity is equal to square root of G over L. I have L, so I just, okay.
So right here, that's
4 pi L. 4 pi square L over T square. Time period square.
So do you use 56 centimeters or 0.56?
0.56 meters.
Okay.
So, okay, one thing you should be quite good at is, not good at least you should know that, is be consistent with your dimensions units. So if you are using centimeters at one point in the question, use centimeters everywhere until the end, at every point in the question. But I suggest always to use a SI system, so use meters, seconds. You can use light years if you want. On this planet, the next question is, on this planet, find the pendulum period if you double the Bob's mass. I don't know who Bob is. Find the pendulum period. Okay. So if you look at this equation, it is independent of the mass. As long as the length and gravity remain same, we don't really care how much Bob weighs. Okay. what he's eating every day. Okay.
So it doesn't matter.
No. So independent, it's the same value. Time period remains constant, which is 0.41 seconds, which they gave us. Oh. That's a fun question.
I'm still confused on C.
About
So is that 2 pi times square root of L over G?
let me rewrite it just here. Or you could also write it as
Oh, okay, so you just switched L and G because you were dividing originally. Because the
No.
equation's 2 pi over omega, so it would be 2 pi over the square root of G over
G
L.
over L, which
Okay,
will,
so that's what I'm saying. So
Oh.
you just switched up.
yeah, I think I showed that to you, no? I thought it.
No, that's why I was confused.
Yeah, so yeah, that's what it is.
Okay.
Where
Yes.
did you switch it?
Oh, so the formula for omega is square root of G over L, and omega is equal to 2 pi over T, or in other words, T is equal to 2 pi over omega. So when I divide this, square root of G over L, I'll get 2 pi times square root of L over G.
For like A, it tells us it was initially displaced by 0.087 radians. Does that just not matter? You can figure out
Oh yeah. So yes, the initial displacement really doesn't change the frequency or angular frequency or time period. Initial frequency, initial displacement just tells you what amplitude it can have, not frequency. Frequency is independent of those constraints. It just depends on what the system is made of, the mass. In case of pendulum, you have mass. Sorry, in case of spring, you have mass. In case of pendulum, you have length. Any more questions?
What was the answer to C?
1.1.5.
Okay, so 1 3.
1.31.5. Oh, that's what I got.
Yeah.
Yeah, that's what I got too. I just
And then the answer for D is point.
0.41. It's the same because it's independent. It doesn't change. Yeah. So the answer for C is 1. Let me write it down for people who aren't here. That's by the way, 130 meters per second square. That's hell of a lot of gravitational acceleration due to gravity. It's more than Jupiter. It's more than any planet in the solar system. Jupiter, I think, has like
We can,
4 Gs.
but we can calculate a planet's mass from that.
No. Yeah, mass, yes. Yeah. Yeah. And if we are given the radius, we can also calculate.
Oh, yeah, see where that's no problem.
So in the exam, if you are given, if you are asked to find out the mass, and if you know gravity, using the same formulas that we used, gmm over r square, using that.
Yo, please do.
Not g. Okay, gm over r square is equal to.
It doesn't matter. It's in the
Yeah, no problem. Oh, it's okay.
Yeah.
In this case, r is the radius of the planet or the location itself.
period. It's on this plan. It's on this plan.
The third question is, so don't take this to scale. This is supposed to be 10 degrees. That looks more like 30 degrees. And the length is, well, it's a meter stick. Okay, the question the question says 0.25 kilogram meter stick is fixed at one end, so it can swing freely in a vertical plane. So it can swing like this. It is initially held 10 degrees below the horizontal. So that's the horizontal, that's 10 degrees below horizontal. Find the angular acceleration when it is let go. So when you're asked for angular acceleration, most of the times what you end up using, what you would use is torque. So we have a formula for torque, which we have discussed a couple of times in the lab too. Is I. So using these two equations, we can, if we know what force there is and what's the radius at which the force is applied, or distance at which the force is applied, we can find out torque, which we can use in conjunction with the moment of inertia to find out angular acceleration. So going back to all the way back to your forces and free body diagrams, let's see what forces this thing has. So let's see. No. So there is a force due to gravity, mg. M is mass of meter stick, we already know the mass. And since it is held here, it also has, it essentially is like a rope which is being pulled by its mass. So there is a tension that this, let's call it ceiling, acts on, okay, there is a tension in the rod that is being acted upon by the ceiling because of its being attached there. So that is this direction. So now you're asked for the initial angular acceleration. So that's the initial position. Again, that's 10 degrees. Let's move to next page. Before putting in the values, let's see what moment of inertia of this rod is. So let's take a rod. Something. So through the center, if you rotate a rod like this, the moment of inertia is 1/12 m L, the length of the rod square. Since it's through its center of mass, I call it ICM. But in this case, the movement is about one of its corners, ends. So using parallel axis theorem, so that's parallel for lazy. Does anybody want me to explain parallel axis theorem? Yes. Okay. So if you know let me write down the equation. moment of inertia I through some point somewhere is equal to moment of inertia through the center of mass of that body plus mass of that body times the distance from the center of mass to the point where you are calculating the moment of inertia. So it is probably easier to understand with the example. So in this case, the center of mass is here, and we are considering the point here, which means, well, okay, just making clear, axes are like this. This is the center of mass axis, this is the axis of the edge. So using the same formula, ICM is 1 over 12 ml square plus, let me make a small adjustment. Ha! 1 over 12 ml square plus m multiplied by the distance from the center to the place where we are calculating center of moment of inertia, which is half of the length of the stick, so 1 over 2 L whole square. So I through one of its edge is 1 over 12 ml square plus 1 over 4. When I square 1 over 2, I'll get 1 over 4 ml square.
Is that multiplication sign or X?
Oh, this one?
No, okay.
This?
X.
Oh, this is multiplication.
Oh, it's okay.
Oh,
Oh. When you are confused about what a sign might be, it's easier if you look at the dimensions. And if dimensions are consistent along all the parts of the equation.
Can I ask a question? Why, okay, with the moment of inertia, you were saying like it was going, yours, the center mass going this way, but this one, isn't that going like this?
Yes, that's why we are calculating center of mass through one of its edges.
So as in the edge going this way though? Or it doesn't matter?
If you think about it, it's it going this way or it going this way.
Oh, okay, it's
At
the
the
same thing.
It's just the orientation is different.
so the 1/4 ml squared covers it not being at the center of mass. Okay.
And if I add this 1 over 12 plus 1 over 4 is 4 over 12. So that will be 1 over 3 ml square. So you might have this in your cheat sheet or the formula sheet, equation sheet, but this might be useful, just the idea of using parallel axis theorem and deriving. Oh my god, that's a 10-degree angle. This is a 10-degree angle. Okay, so coming back to the question, part A of the question. Oh, we did not do the fun part yet. We saw that, I think here, no. The forces acting on the rod are mg and tension. And we are trying to find out what's the torque about this point, because that's the point about which it's moving, and we want to find out acceleration, angular acceleration about that point. So this tension is going through that point, so it's not going to give any torque, because torque is r multiplied by f. R is the distance, perpendicular distance from the center, well, from the point where we are calculating the torque to the force. And in this case, the force is basically going through the point, so it's 0. The distance is 0, which is why torque is 0. So the only torque, only force that is contributing for the torque is mg, and keep this figure in mind, I'll probably draw it. 10 degrees. Mg, so torque is equal to R cross F. In this case, remember that R, well, the cross product of cross product is of two vectors A cross B, or in this case R cross F is RF sine theta. Okay. R multiplied F. Let me sine. Let me write theta. I'll tell you why theta is whatever it is. So R in this case is, oh, just to be clear, since we are writing sine theta, it's just magnitude of R and F. In this case, R is the distance from the point of rotation to the center of mass, or the point where the force is being applied. So this distance, which is 1/2 L, multiplied by force is mg, and theta is the angle between R and mg. In this case, R is from this point to this point. So the angle between this and that is, this is 90 and this is 10 degrees. So this is 90 minus 10. That's 80. 80 degrees.
Wait, where are you? Okay. Sorry.
That's all right. It's, I am, actually, let's see if they have a,
What are you looking for?
I'm looking for a thinner size.
Yeah,
Yes. Yeah, find it out at the end of the session. Not end. Okay. So
you were seeing the angle. You were trying to
this, that's the horizontal.
Okay.
Okay. That's the bar,
Okay.
and just representing it with a line. This angle is 10 degrees. We want we essentially want the angle between R, which is directed this way, and mg, which is directed this way. So that is 90, the angle between horizontal and vertical, minus 10 degrees, the angle the bar makes with the horizontal.
Oh.
So that will be 80. So L is, this is a meter stick, so it's a meter in length. M is 0.25 kilograms. So also, I have noticed people sometimes making mistakes of using radians instead of degrees, and degrees instead of radians in calculator. So make sure you have it right. Oh, actually,
Mass is 0.25. 0.25 over 2. And 2.
Length.
And length is 1.
Oh, it's one.
Length is 1 and 3.
yeah, it is a test, but it was the test.
Oh yeah.
Can you write your name down? If you don't have a problem, your email. The second question is,
What's the
wait,
answer?
Well, I didn't know if we were going backwards or, you did hit me in the face, so I'm still pissed about that.
Did anyone calculate that?
I got 1.2.
I got,
Yeah, it's 1.21, and then
Okay.
you equate it to inertia times.
One of you used radians instead of degrees because you're giving different answers.
We both said 1.2.
Oh, you did? Someone said 4 points. Okay, 1.2. That's the torque.
What's the units on that?
Newton meter. Newton meter. Assuming that you have used a SI system. Yeah, 1.2 makes sense. So that's the torque that due to this force, but that torque is what gives the rod the angular acceleration. You can imagine it as like a force, but in case of circular system. So force gives acceleration linearly. We say force is equal to m times acceleration. The same way in circular systems, you say torque is equal to, instead of mass you have moment of inertia, instead of acceleration you have angular acceleration. So, and most of the formula actually have analogy between linear and circular systems. For displacement you have angular displacement. For velocity you have angular velocity. For acceleration, angular acceleration. Mass, moment of inertia. Torque, force, torque. But I don't think taking it more than that is not a good idea. I mean, I think it's not a good idea. I don't think it's a good idea. So we know torque is I alpha, but we already figured out the formula for I, which is 1 over 3 m L square.
Bigfoot 3 for people online.
Sorry?
Bigfoot 3.
Oh.
1/3 of those guys.
No, oh.
Yeah, that's what I like.
So much better.
Okay, it's 1 over 3.
1 over negative.
That doesn't look like a negative 3.
You should probably change the
you should
signs
make
of
your
your.
eraser smaller.
Yeah.
Just make, no. That's what, okay.
He doesn't care anymore.
The screen's out of calibration if you make
Yeah,
it look at
yeah.
the bottom left.
L is 1, M is 0.25. So this is equal to 0.25, 0.0825. Am I right? Alpha. 823. 833. Okay. My mistake. Whoa.
Wait, we're starting for alpha, aren't we?
Yeah. So I am just writing down this part of the.
Oh, okay.
So you see it's like 1 meter, right?
0.083, okay, yeah.
So we just equate these two,
And you
torque and torque.
And you get 14.4.
14. If you say so. 14. Yeah, 14 points.
Actually, I mean, yeah, I just only said 14. 2 yeah, we only use 2 sigma is 14.
14.4.
0.5.
It's
14.4 something.
5.2.
I didn't even get a fourth number.
It should just be.
I mean, shouldn't it just be
2
14? Because it's
Yeah.
2 sigma.
Yeah. Radians per second square. Let's just for the fun.
regional, right?
So most of the times when the second part asks for angular velocity when the meter stick is in the vertical position. So when the meter stick is moving down, uh, at the bottommost position, they're asking for angular velocity.
So when it's like at 90 degrees, is that what
When it's at 90 degrees with the horizontal. Okay, so we can use conservation of energy, which this doesn't matter.
Yeah, wouldn't the forces directly oppose each other at that point?
Sorry?
Wouldn't the forces directly oppose each other at that point at the vertical position?
Yes, they do.
Okay, so they would cancel each other out.
At that point, yes. Tension changes at every point. So we cannot really use that as a. That was the initial position. That's the final position in retrospect. I would think. Okay. So yeah, what do we want? Energy, conservation of energy. So the energy at initially the energy is let's take this point, the center of mass, as our reference, as our zero potential energy, or we could also take any point as zero potential energy, but it's easier if you choose some either initial or final position. So we can choose the initial position as a zero potential energy point, reference point, in which case the energy at this point is sum of kinetic and potential energies is 0 because it just starts moving, plus 0 because that's the reference that we chose. You could also choose this as your reference, in which case the potential energy is mg times this distance. So choose one point, one level.
Which point is where 0? The initial position?
This point, yeah.
Yeah, why?
Because potential energy, that I said this is a reference, right? So a reference is a point where potential energy is 0. By definition, that's
Okay.
0
But why is kinetics? Oh, because it's not moving.
because it just starts moving.
Okay.
Let me not confuse you. Let's do with this point. Let's
So the only difference between those 2 points is just height?
yes.
Okay.
Let's
Make it tinier. You can make the thick.
I know. Go through all that. In which case you have potential energy not equal 0.
Okay, you're switching it to now the bottom.
Yes. So I just switched the
Okay.
the origin or the reference to bottom so that
Okay.
people don't get confused. So we need to find out what this level is, the height, to get what's the potential energy, what's the potential energy is. So we know that this angle is 10 degrees. Consider this triangle. We know that this angle is 10 because this was 10, or you could also say this as 80. Doesn't really change anything. Using that and the length, since it's a meter stick, this is 1 meter, L equal to 1, which means this height let's call it H1, is if I use this angle, it's L sine theta or L sine 10 degrees. In this case, 1 multiplied by sine 10, which is 0.0, a very small value, 0.087. That's a little too far.
Why?
Are you sure?
Yeah, I don't think so.
No, not
I
right.
got
0.17. Yeah.
Okay.
I think you're in radians now.
Yeah.
Let me.
Yeah.
You're gonna double check.
Yeah, I got it too.
Oh, he's not in radians now. Otherwise, it'd be negative 0.544. I don't know what you did, but it's 0.17.
Okay. 0.17.
No.
Yeah,
point-
0.1.
Yeah, yeah, yeah.
0.17. Just sine to 10. Is the answer sheet incorrect?
We were getting wrong.
If I
answers.
did something wrong.
That's what we're about.
Because it should just be the sine of 10, right?
Yeah. Yes. That's weird.
That does sound like an earlier answer.
Never mind. Ah, I see. I see why I got. Okay.
Go back and redo all of the other answers.
No.
Is it because you used a different reference point?
This was the center of mass that I'm using. Remember?
Not the full length.
Not the full length. The full length is 1 meter.
So
The
it's-
center of mass is half of the length. So I have 1 over 2, which is
Okay.
0.8087.
Just because the force is at the end instead of at the middle.
The force is at the
He
middle.
was trying to find how, like,
So what I'm doing right now is, what we are doing right now is energy conservation, right? So when we are doing energy conservation, we are considering in this case the bar to be a point, and the point a point mass. A point mass when we're considering is always at the center.
Okay.
So in this case, the center is at half.
Okay.
Can I quickly ask you a question?
Yes.
Can we go up a
Wait,
little
so
bit?
that's half.
So, well, not that much, because I need to see the triangle.
Oh.
Sorry. Okay, so what I'm questioning is like, where is this triangle? Is this like the whole meter stick right here?
Yes. That's the center of mass.
So there's an
Because
H2 down
the
here,
force
so you
of
see how like
Yeah.
on the
Yeah.
first one,
So
there's H1 up there.
this was what we calculated until now.
Oh, okay.
So
And
we're
then there's
using the
another
total.
H
Yeah.
on the bottom.
So you're just looking at
Yeah.
Okay.
So we got H1 is equal to 0.087 meters. And we know L is 1 meter. From this figure, we want this height. That's what we want because that's what we use for the potential energy. So that height is 1 minus 0.087, which is,
0.93.
oh, sorry. Sorry for the confusion. Again, remember we want the center of mass. We are worried about the center of mass position, not the end of the bar. So we don't want 1, but we want 0.5. So if this is the center, great. If that's the center of mass, this is what we want. If that was H1, this is what we are worried about. That's what we are considering.
So, okay, so we took the meter stick,
Yes.
and we got it in half,
Yes.
and then there's an
No.
H1 and another H
Yes.
in that half.
The H1 is the projection of this half. It says the vertical position.
It's how much higher the middle of the yardstick is if you pick it up.
Okay. Yeah, it's okay if you take the stick
Yeah.
and you take it at an angle of 10 degrees, which it was initially.
Yeah.
This point, which was the center, has moved by this distance, right?
Yeah.
So this height is what we are. This height is what we are considering.
Is that H or H1?
This is H.
Okay,
This is H1.
got it.
So
I'm so confused.
that is 0.423,
Whoa.
So you wouldn't be like on it. Or 130.
which means
0.42.
U is equal to mgh 0.25, 9.8.
It's 413.
Yeah, why do you have 423?
Because I am really very intelligent. And that is, I let the experts deal with it. The calculation part.
What is
your
it?
father
I'm not sure
question?
about that.
So H1 is the first. Is this part right here? Zero from here.
To give you a better idea.
Big moves.
This is H1.
I got 1.2.
And this and this.
1.01, yeah.
Good enough for me. This is the same. That is H.
Okay, maybe this is H1.
Yes. No, that
What
is
would take
that
the
over
kinetic
to
energy?
0.087
Which
H.
You
Use to remove.
Okay, so it's over.
I'm trying to get into
Is
this.
H1.
Okay, so it's right here.
Uh-huh.
Okay,
Wait, why
and
do
then you took, and then right here it says.
So,
Because we're doing conservation
the length.
momentums to figure out how fast.
Oh, yeah.
It's 1/2 the angular velocity.
So this height is half meter because the center of mass is at half a meter distance from the end.
So H1 plus H
Is equal to half, 0.5.
So H1
And that's equal to 0.
1/2 of a meter. Whatever.
Yes. Let me quickly do this. This was the center. That is H1. And if this has moved down, vertical. Whoa. And the center of mass also would have moved down by some distance. This is H. So H plus H1 is equal to 0.5 meters, which will tell us what H is. And why did we do all this?
Wait, what happened? What is H? Did you guys figure out what H1?
0.413. We all did that. We did all that to find out what that is, which is 1.0.
And then we solved for H1, which was 0.087. Or did we solve for H?
H is 0.413.
Oh, okay.
So then U is equal to K, and K is equal to 1/2.
So that's what we did all this for. Find out what's the energy at that point.
And we still have 0 kinetic energy?
Yep. Because we are worried about, well, this is the initial point. Initially it's at this energy, this potential energy, 1.013 joules potential energy, and 0 kinetic energy. So now, when it goes down,
The units is Newton meters, right?
Yeah, Newton meters.
So you're talking about all these
So, so just to
So we just figured it out. Sorry.
And it's gonna have the same energy as the model, but this time it's gonna have no potential energy. So you're gonna put that one.
And the kinetics are inside.
And, right, not equal to 1/2 pi.
final energy is, well, the same value, but we don't know. The potential energy is 0 because that's where we took the potential to be 0 as. And the final energy can be written as, since, like I said, it's a rotational motion, it's rotating. The energy is I omega square. What is angular velocity? So we can equate. This is a bar removal. We calculated what I was previously.
1/3. Oh.
like 0.083
What was the value of I?
0.0833.
And the answer in the next page.
Yeah.
So we already solved for R.
Yeah. Oh, the angular acceleration.
Okay.
I was 1/3 ml squared, right?
Yeah.
And back in that problem, we also said it equal to I times.
Any questions?
So the 0.0833 is equal to 1/3 ml squared.
Yes.
So 4.9. Okay, 4.9. Hey. That was a neat trade draw. That was happening.
No, they had two. I'm gonna go over
You don't want the short answer as in the first one or the fourth? Both. Well, I was planning to go through both of them.
Yeah,
Yes,
please.
What's the time? It's 7:80. Okay, that's no problem. So what's the first question? Student A holds a disk. Are we done with this? Student A holds a disk of mass m and radius 4r. Student B holds a disk of mass 4m and radius r. Each thinks their disk will be harder to start rotating from west. Which student is right, or are they both wrong, or is it impossible to tell from the given information? So when we are rotating, like I said, if you're moving a body linearly, the force required to move it is ma. But if you're trying to rotate it about some point, in this case about its own axis, sorry.
The radius is what matters more.
No. So I mean, yeah, okay. The instead of force, if you're rotating it, the torque is what we consider. And like you already know, torque is I alpha, right? So I is what matters. So for a disk, moment of inertia is half mr square. And for the first one, the mass is m, radius is 4r. So moment of inertia of A is 1 over 2 times m times 16 r square, because it's 4r whole square, 16 r square. Yep. So it's harder for A to rotate the disk about its axis.
Why did we use 1/12 mr squared on that other problem? So
That's-
That's because it's a rod.
Yeah.
This is for what?
It's a bar, a rod.
Oh. And we use 1/2 for disk?
Disk is 1/2
Okay.
mr square.
All we know is
And sphere is 2 over 5 mr square.
so.
Okay, so it's just a different equation.
Yeah.
Alright.
Whatever. Wait, so are we supposed to memorize like?
Those are listed. So disk A is the one that's harder to rotate because the inertia.
Yeah. So moment of inertia of A is bigger, which means the A guy has to apply more torque to rotate it than I have said in class several times. It's the question. That I believe rolling motion is not only the hardest concept we deal with all semester, but blah 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 blah. The question is, please explain what smoothly rolling, which means no slipping, motion is, and explain how it is a combination of translation and rotational motion.
Yeah, you did say that actually.
You could make these really hard.
Even if this was the test,
What are the odds?
What?
What are the odds of this
Don't touch it, you must know.
being a tangent to the?
As soon as you touch it, it's gonna mine. It's gonna move 2 feet.
So no slipping, rolling. Rolling means it's moving smoothly without slipping, which means this point is the point about which the ball is rotating, and if you actually trace the path of the point here, it will take a path and so on. Cycloid, it's called a cycloid. So this point, the center of mass, when the sphere is rolling, sphere or disk or whatever is rolling, this center of mass is moving like that. Upwards, the radius is okay. It's not changing. It's not upwards. And this point is moving like a cycloid. If you did not have a translational motion, this point would be along the circle, just there, rotating there. And if there is no rotational motion, just translational, this is the only the point here would just take a path like this.
If it was only translational.
If it was only translation.
And if it was only rotational, the ball would stay in place.
Yeah, just stay. So if you consider any point except its center, if you have translational motion, it's a linear motion. The point would be linearly moving. If you have just rotational motion, it would be circularly moving. But since we have both the motions, it's a cycloid. And you don't need to know cycloid.
Can you just quickly repeat that? I'm sorry.
So that's a disk or a sphere, anything that's circular, and it's rolling. It's not sleeping. And when you say rolling, the question has explained why it is both translational and rotational together. So if a disk is rotating, just rotating, this any point on the disk would be moving in a circle, just at that point. And if it's just moving, translating, the point would linearly move. But since, oh, look what we have here. So that's the disk. If you consider the 12, number 12, when I'm rolling, this is what is going to happen to 12. So the point that it traces is not linear or circular, it's a combination of both of them.
Is that, so what's the definition of smoothly rolling?
Yeah, that's what I'm.
It's rolling or
Right.
it's rolling. And when it's rolling, it doesn't slip.
Explain what smoothly rolling, no slipping motion.
I mean, it tells us no slipping, so like
I mean,
rewriting that.
Smoothly rolling, no slipping motion is pretty descriptive. How else can you describe it?
That's,
I guess
you
if it
can
was,
just try.
is it because it
Can we
was
just draw
slipping?
this diagram like?
It would be more
Yeah.
more than it's translated.
Yeah, because if it was slipping, then it would just be transitional.
Yes.
Like, it would just like be going this way.
So if it is slipping, there will be translation motion, just the translation motion. If it's just slipping,
Okay.
if it is, yeah.
That's it.
So the answer
I was gonna say if it's
No, but
rolling,
isn't-
but
isn't
I
slipping like when the car tires, it's rotating more than it's actually moving forward.
What
Yeah.
he's saying,
So-
this thing is not slipping, but it is
Slip-
moving.
No, rolling ball
partly
is
bowling. So when you actually
Then that
bowl
point
right
is
away,
the cycle.
the ball slips
And
for a
that
while.
cycle
Yeah, and
is
then it
once
rotational,
at some point,
both
once the
translational
friction is enough,
rotational.
uh, once the speed is just enough, not too much, but just enough for the friction to kick in, that's when it starts rolling.
So slipping is
Oh, it's like
Only
a tire
translates.
burning out.
Yes,
That's
tire burning is slipping.
Yeah. Okay. Before it catches the coefficient of kinetic friction.
And yes, and at that point it moves forward. It's
Imagine you burning out on
Is that maybe what we're
How
talking
long?
about? Center mass
Right.
is-
Yeah.
let's have a
the ball is not
descriptive
rotating,
class.
but it's moving.
This is fun.
So yeah,
That's
so
opposite.
slipping.
Let's try this.
Yeah, I don't know.
It's not even.
That's not going.
Oh, wow.
Oh, great.
Don't touch it.
That's a game.
Like slipping
Yeah.
when you're
Yeah.
burning out your tires.
It's
It's
just
just
like
like
it's
it's
spinning
spinning
in
in
place,
place,
but
but
it
it hasn't caught the friction yet to start
So
going
pretty much
forwards.
the distance of the circumference is equal to the distance of the translation. That's no
But yeah,
slipping.
basically. I don't think you need to go that in depth, but yeah, it's just saying.
That's cycloid.
If it's yeah, so if it's slipping, it's only rotational motion, not translational.
No, it's the
No,
rotational,
it's
it's
going
going
around.
around the translational.
Okay, fuck this question. Move on.
So slipping, transitional,
Are you
and then rotating.
I am ready for this.
Okay.
Oh, you are grading?
So just in case
Oh,
if we
okay.
get this and we explain it the
No,
way.
I mean, it will go through him, but. And don't be sure that this is what is going to be the test. Just saying.
It could be another monkey in a tree.
It could be, yeah, it could be like
Yeah,
one,
monkey in
the
a
one
tree.
question that would be on
What
there.
if he's watching this? Like, okay, now I'm gonna change it.
He could be one of the students. Or one
Be
of
the only student watching it.
Usually these things. never
Alright,
go.
so why is slipping only translational?
That cycloid shape it traces is the combination of translational
Right.
and rotational.
Uh-huh.
That's what he's asking.
I also doesn't explain what smoothly rolling knows.
Isn't
Just
smoothly
draw
rolling,
the
Okay.
the
picture should be
distance of
good.
the distance
Okay,
of the
okay.
ball rotating.
Let me explain it this way. Smoothly rolling is rotation of the body about this point, the point of contact. So when it's smoothly rolling, the ball rotates about this point, and as it moves forward by a little bit, the point of contact changes. So for each and every point, the torque applied is about this point, and the torque, the force that this torque, the force that gives this torque is the friction. If you want, you can add that. So friction gives it the torque that it's needed to roll, and that's at the point of contact at every point of motion.
What is the point of contact?
Okay, so this is the point of contact.
So we're just picking one point.
No, we
No,
it has to be.
well, we don't get to pick.
Oh, I mean,
So,
When it contacts the floor.
okay.
so okay, at this point you have frictional force,
Yeah.
right?
Yeah.
And the frictional force is giving the ball or the sphere or whatever a torque about its center. That's the only force that is acting, which is not passing through the center. You have mg, but it's passing through the center. So torque is due to the friction, which is acting at this point, but that point is not stationary. It's moving, and at every point of its motion, the point of contact changes. So every point in a sphere acts like at some point it is being acted upon by frictional force, which gives it the torque. Is it clear?
No, that's what I was asking.
So smoothly rolling is basically it's the distance that the point goes by the circumference is equal to the distance that it translated.
Yes, yeah, that's true. So this length, well, that's let's try to see.
So what I said is okay.
Yes,
The point with the circumference.
Yeah, so how much the circle, like the circumference of how much it rotated is equal to, it corresponds to the distance that it rotated. That makes most sense to me.
Alright, on to the multiple choice.
Wait, I still don't know how to answer this
I'll
question.
tell you later.
Okay.
The first multiple. Everyone's clear, right? No other questions. Okay. The first multiple choice question is: which statement about R square is true? Option 1 is R square is used to compare measured data to theoretical prediction, which makes sense for people who
I'm sorry.
R square.
It's
The answer is
linear
I.
approximation.
Yes.
So why is the answer I?
But I'm going to talk about the others.
Oh,
For multiple choice question, you don't have to know that one option is right. You can also know that others are wrong. So the second question, second option is closer an R square value is to 0, the better the fit. Not necessarily. Not it's. No, I mean not necessarily not. Sorry, it's wrong because R square equal to 1 is the best fit. R square is 0 is actually opposite to the best. It's the worst it can get. The R square value for R square is y-intercept of a linear fit to the data. Okay, let's just talk about what R square is. R square is the it's not necessarily linear. It's the correspondence between measured data and theoretical values. So if you, for example, in your labs, if you had a plot which is supposed to give you an answer which looks like that, for example, and your points are like this, so that would give an R square value of about 0.9 maybe. It's not a perfect fit, but it's not completely off either. So if you had data like this, you will probably get a 0 because it's not correlated at all. So R square is just a comparison between your experimental value and theoretical prediction. That being said, third option is the value of R square is the y-intercept of a linear fit to the data, which doesn't even, it's not related at all. Fitting a line to data that follows a quadratic relationship will always give an R square value of 0, which is not right, and it's too long to be. Just kidding. The second question is Any questions? I mean, it's just a definition.
So it's I.
Yeah, first one, yes. The second question is consider a simple harmonic motion. Simple harmonic oscillator made by attaching a block of mass to the end of spring constant k. The block is initially stretched to a distance a beyond spring's natural length and let go. Which of the statements is true? So you have a spring constant k, a mass of m is attached to it. You pull it by some distance and leave it. So it moves, oscillates about that default position. Its default position. They're asking, well, which of the following statements is true? First statement is period of oscillation will be k square root of k over m. So if you remember from the second question, I think, yeah, omega for a spring is square root of k over m, and time period is 2 pi over omega. So square root of k over m being the period of oscillation is wrong. Second question is position of spring will be given by x is equal to a. X is equal to a cosine square root k over m t minus pi. In questions like this, it's always the simplest way to do it is substitute 0. At time t equal to 0, we know where it is, where it was. We pulled it and left. So at time t equal to 0, it should have some distance from x. So the x should be actually equal to amplitude because that's the amplitude with which it moves.
So at time 0?
Yeah, at time 0.
So yeah, that's.
The time 0x should be equal to A. Right.
Yes, because okay. Let me just explain a little bit about simple harmonic motion, simple harmonic oscillation.
No.
No, because negative
It would give you 1.
Cosine
Yeah, negative
x
pi
equals 1.
Negative pi. Yeah, so A. So it would give you.
No, it will give you 0. Wait, I.
Cosine
No,
of
cosine of
pi.
negative pi would be 0. So cosine of 0 is 1.
No.
Oh, negative pi. It's still negative 1. Yeah.
It's negative 1.
Yeah.
Yes.
So we give you negative A.
Negative a.
Okay. That's fine.
So that's wrong. The third part is magnitudes of position and velocity of block reach a maximum when the magnitude of block's acceleration is minimum. Okay, so when we pull it and leave it, that's the maximum position. And that's when it has the maximum acceleration. That's when it's being pulled by the spring a lot. When it's at its center, there's no pull from any direction on the block. So acceleration is how much it is being pulled by that, but not
So they're
exactly.
directly proportional instead of just inversely proportional.
Yes. Directly proportional is not the. Yeah, it is directly proportional.
Okay.
Always remember, in simple harmonic motion, the position is directly proportional to acceleration. So that's not right. Doubling the initial displacement has no effect on period in block's motion. So this is something we discussed already. 2 pi square root of k over m. Or wait, m over k. So the question says initial displacement. So this doesn't have initial displacement anywhere in it.
I don't think that. No, the cosine of minus pi was negative.
Well,
It's probably fine. You were saying about the doubling the initial displacement. So it's independent of initial displacement, and so that's why it's
yes.
So we're saying they're all false.
The
No.
last one is true.
The fourth option is true.
Oh, it says it has no effect.
Yeah, it doesn't have any effect. The third question is, a solid sphere, disk, and hoop all have same mass and radius and are all released from rest at the top of an incline. They all roll without slipping. What is the order in which they arrive at the bottom of the incline? So let me mark this as solid disk or hoop, sphere, disk or hoop. Just all of them look the same from this direction. Anyway, so order of magnitude which they arrive. Okay. So what we can use in this case is we can use the conservation of energy, and we can say that mgh is equal to mgh at the top, this point is equal to actually half I omega square plus ls. That's all we have. No, I mean half I omega. So all the potential energy is converted to kinetic energy. Mass is constant for all of them, so mass doesn't matter. We want to find out what's the maximum velocity. So we see which of them has the least moment of inertia will get down faster, get down the incline faster. So we just need to know what the moment of inertia of each of them are. For a sphere, it's 2 over 5 mr square. For a disk, it's 1 over 2 mr square. And then for a hoop, it's mr square. Let me just write them down. Remember, this is through their center. All of them is through their centers. Yep. So in this case, sphere has the least moment of inertia, so that will come down quick. Oh, and the second is disk, and the options ask for the order. So sphere, disk, and hoop.
So it's the spheres first, second.
Yep. The conditions. Okay. The conditions. The next question is the conditions that the net external force and external torque both vanish. So we have to see which one of them is true. The first option is holds for all rigid bodies. If I'm moving this chair, it doesn't have net external force as 0. So it's a rigid body. So that doesn't have to be true. In most of the cases, it's not. Can never both be simultaneously satisfied? Yes, it can be if it's not moving. They both of them can be at net zero external force and external torque. Are true in branch of mechanics known as statics. So statics, by definition, is dealing with is that branch of mechanics which deals with objects that are stationary and on which no external forces and no external torque is acting. So statics net. write the so when I say sum of inputs, that will give us an output. Actually, just to be clear. And fourth option is true only when torque is computed about the center of mass. Not really. I mean, even if you compute torque about center of mass, it could move. In the case of rolling, it's moving about the point, and it's moving about the point of contact, and it's moving, so it's not zero. And forces, obviously, about the center of mass.
So it's 3.
The 3 is the answer. So the last question, yay! As the ice caps at north and south poles of Earth melt, the water will spread itself approximately uniformly in a shell around the whole Earth. As a result, the Earth will spin slower. This is an example of equatorialism. Yes.
The conservation of energy.
No. Conservation of energy.
Oh, yeah.
That's what so we want to do stuff.
So the first question is conservation of energy. It's not really. It's not conservation of energy. Conservation of energy doesn't. That's what you're going to write in the test. Parallel access theorem is. I don't know how it's related really. To this question.
Yeah.
It doesn't make
So
sense.
conservation of the mass.
Conservation.
Moving it closer to further out.
Equalitarianism.
Yes, but that doesn't. It's not a. It's not a consequence of parallel access theorem. They're asking. The question is asking: the Earth will spin slower when the water spreads out to its center, towards its equator.
Those like the balls.
Think about the professor sitting on the chair spinning. Lose the
Oh,
light.
screw that, man.
Exactly, the same idea. You actually use this concept
Yeah,
for your
kind of.
last lab.
Yeah.
When it's moving, at some point it slows down, the ball comes down, and the
Took a picture.
angular velocity increases. So when the mass is closer to the center, the angular velocity increases. When it's away from the center,
That doesn't look very.
when I'm saying center about the axis, I'm talking about the axis. So all the north and south polar ice caps are close to axis, very close to its axis of rotation. But when it spreads out, it's moving away from the axis, which increases the moment of inertia, which decreases the angular velocity. So that's the basic formula for
So conservation of angular momentum.
B.
How's it true? I know.
So, when you say.
I can't really read it. The comic. I want to
be able to do
comic.
that,
Oh, it's,
right.
the
I can't
moment.
read it.
It's they're talking about moment of
You have another
inertia.
final, right? So you're.
Meanwhile, the moment of inertia for US is
I got one
the first nanosecond of summer vacation.
Yeah, then I got this one. I pitched my bio final.
Oh.
So I didn't take that one. Then 5 finals. I only have like 12.
All right, guys, all the best for the test.
Is that a half?
Hey, grid is.
See you on campus at some time.
Wait, so does he?
I still
grid
got
is
my house.
Yeah.
Yes. You and
Max.
So, there was no status question on questions on this, but we expect a status question on the.
what do you mean status?
Do we have office hours?
There's no
He's got
question
something in his own
on
English.
the status.
Nah.
Oh, you mean? Well,
No problem, there's like a multiple choice question.
I'm just going into it.
It's just, if you can actually solve this problem, solving statistics, you use forces, you use torque. For example, in the case of the bar,
I didn't see it.
use the keyword use force and torque.
They took it down.
But you were the portion of the exam, you finally took it out.
So apparently the smalls they have
Oh,
like
it's a Swedish government.
Yeah, they rated it.
so the smalls like have their own island.
Static.
So the, well, keep in mind, the important part of, I think the test is,
There we go.
there we go.
Wait,
Yeah, that's what you should say. I said the important part of the test.
That's your kind of question.
The topics that you need to prepare for the test, most importantly that you've seen here, are
So are they gonna be similar?
circular motion. They're going to kick you if you talk right now. They want the answers. Circular motion, rotational motion, simple harmonic motion, all kinds of motions. I think that's all. That's what this topic covers.
So we don't have to worry about any previous topics.
No, because it's just chapter 12 to 15, including 9, which is
So, if you have any questions,
Ask now for the whole piece.
no, you can send me an email.
Do you have
If you have any question about, if you want your labs, let me know.
Yeah.
I've graded them. I've put them in my office. Here.
Did you update all of them so far on?
I think I did not upload the grades for 2 or 3 people who submitted it.
But everything else should be on there, right?
Yes. And also I'll upload probably tonight or tomorrow. I'll upload screen final score. So that is 10 labs, just the 10 labs, the average of it, and then all the other scores. So you'll know where you stand.
Go ahead. So you said you dropped 2 labs,
Yes, I drop 2 labs and then put the score.
and then you're the one grading the exam.
It's a 2-stage grade, so I'll grade it.
Yeah, like your grad starts my section, but I'd only missed 1 lap, so that's why I thought I
You don't.
Okay, good job.
We couldn't figure it
Let
out.
me-
Like, if we get, I don't think we collected the right data. Like,